All right, today we're going to continue our deep dive into the world of limits. And I want you to start by evaluating this limit as x goes to 0 of the cosine of x. And you can use any method you want. So if you want to use a calculator, look at the graph, you could make a table, or you could try direct substitution. Do that, see what you come up with. All right, so the easiest way of doing this is actually direct substitution, and that's what we'll be doing today, just looking at some trigonometric limits. We haven't really talked about these a lot, but they function in most cases very similar to what we did with polynomials, and that is you can just directly plug this in. So the limit as x goes to 0 of cosine of x, you simply just replace the x with 0, so it is the cosine of 0. You then have to think, well, what is the cosine of 0? And that is 1. So that is by far the easiest way. Another way would be, well, you could plug values into a table. You could plug in, let's say, 0.01, 0.001. You could plug in negative 0.01, negative 0.001. See what those are approaching. When you do so, you do get values that are approaching 1. You get 0.999. This one you actually get 1 if you do it in the table of your calculator. Probably get similar results, yep. So you can clearly see by making a table as well that these do approach 1. If you also looked at the graph, you could see that as well. The function is clearly approaching 1 because the cosine function looks like this. So as you approach from this way or this way, you are approaching the value of 1. So today we are going to be spending this lesson talking about trigonometric functions, and also we'll look at exponential functions as well. This necessarily isn't any more difficult than what we've done before. It's just we haven't really talked about a lot of trigonometric limits. So these are, we'll call them more limit properties, in the same way that the limit of a polynomial, well, you just plug it into a polynomial. The same is true for any trig function. So the limit of the sine of x as x goes to some constant a would just be the sine of a. Would be the same for cosine as well. You're just going to plug it in. It would be the same for an exponential. So the limit as x goes to a of e to the x would simply just be e to the a. Would be the same for a natural log function as well. The only restriction here is, of course, a has to be greater than 0 because you can't plug a negative function into a natural log. The same could be true for inverse sine function. We would just simply plug it in. Same for inverse cosine, and same for inverse tan. Now, a couple things. For the sine function, this, if you remember, also has a tie to the cosecant, because that is just the 1 over the sine of x. So we can also evaluate cosecants in that way. And for cosine, remember that the secant of x is 1 over the cosine. So that can also be evaluated in the same way, right? And also, we didn't mention this here, but the tangent of x is sine of x over cosine. So we can use our limit properties to distribute it in here. So for instance, if we're talking about the limit of the cosecant of x, well, we could do limit of 1 over the limit of sine using our limit properties. Same with secant. We can do limit of 1 over limit of cosine. For tangent, we got limit of sine over limit of cosine. So these general statements apply to a number of other cases as well. Now, it can't always be said for inverse functions. Inverse functions behave a little bit differently. If you're unsure about those, you could always graph those. But in general, you're probably not going to be asked a question about like the inverse cosecant. That's not really a question you're going to be asked quite often. So don't worry too much about these inverse functions. I'll try to throw a couple examples at you just so you get a little bit familiar with them. But again, don't get too psyched out about those because they are a little bit more rare functions. There are some domain restrictions on these sines and cosines as well. For example, this a has to actually be between -1. Sorry, that should be +1 and -1. And same with the cosine as well. It actually has to be in between those two values. Actually can be equal to it as well. The number that you plug in, because if you remember, the inverse kind of just flips the domain and the range. So if the domain of sine is all real numbers, the range of the inverse sine would be all real numbers. Now the range of the sine, let me write this out. So domain of this is just kind of a refresher on how inverses work. So if the domain of sine is -infinity to +infinity, but the range of sine is -1 up to +1, because remember sine looks like this, right? It doesn't go above 1 or doesn't go below -1. So if that's the range, well, the inverse has the opposite. The domain of the inverse would be -1 to 1, and then the range of this would be -infinity to +infinity. So the domain is what we're allowed to plug in. So this fact implies this, that we can't plug in numbers other than numbers that fit in that interval -1 to 1. And same applies with the cosine. It has the same domain and range. So remember, the inverse flips the domain and the range. All right, back to the limit topic though here. Let's just start by doing some basic ones. So if we wanted to evaluate the limit of the cosine of x as x goes to 0, we're simply just going to always try this first. Just plug it in. So that's going to be the cosine of 0. Now this should be something that you should not need a calculator for. These will be questions that are going to be on the AP test that are going to be in the non-calculator section. So you can't just flip your calculator, punch in cosine of 0. You need to know off the top of your head what the cosine of 0 is. You also need to be able to figure out, hopefully relatively quickly, because it is a time test, and which brings me to a little bit of flashback from last year. If you had me for pre-calculus last year, you will remember at one point I made you memorize the unit circle. If you had a different teacher last year, this may not have been the case, so it might not be as familiar to you. Even if you did have me last year and you memorized this, you might have forgotten some of it. But the reason why I wanted you to memorize this last year was because in calculus, you need to know this off the top of your head. You can't plug it into your calculator. You're not going to be given this formula sheet that has the unit circle on there for you. You need to know what these values are, just again by thinking and remembering what the unit circle looks like. For the unit circle, as long as you can generally just memorize the first quadrant, you're pretty good. One key thing to remember also is that the x-coordinate, so like here, represents the cosine, and the y represents the sine. So that is true for all of them. So the x is the cosine, the y is the sine. That is important because if, again, just a refresher, if we're asked to find the cosine of 0, what we do is we find 0, and we'll always be referring to radians and calculus as well. Everything is taught in radians, with maybe a few exceptions, but radians are always what we're generally talking about, you can assume. You go to 0, okay, the cosine of 0, you want to look at the x-coordinate. So the x-coordinate at 0 is 1. So the cosine of 0 is, in fact, 1. And that's all there is to it. And that would be true also if you verified this graphically, because you know, hopefully you have a good idea, a picture in your mind what the cosine function looks like. Remember there it crosses up at 1. So we're saying as we approach 0, this is 0, as we approach 0 from either direction, the y value is approaching 1. So you can confirm it with a graph, but again, you should be able to do these just intuitively by direct substitution. So the next will be very similar. This is the limit of a trig function, so we're going to just direct substitute it in. The sine of pi over 3. So what you need to be thinking is not typing this into the calculator, but thinking in the unit circle what the coordinate pair is for pi over 3. And then it's the sine, so you want the y coordinate at pi over 3. So this is what you should be thinking in your mind. I want the y coordinate at pi over 3. You also might want to picture this in your head. You might even want to draw this out when you take the AP test if you don't memorize it well. Just at least draw out the first quadrant there. So in this first quadrant, we always divide it in this way. We've got 0 here, right? This is pi over 6. This is pi over 2. This is pi over, oh, sorry, I said that wrong. This is pi over 4. And this is pi over 3. And this is pi over 2. So those are your values. Remember, you add 1/6 pi plus 1/6 pi plus 1/6 pi, and then the middle one is always a quarter pi. So it might be helpful to at least write out that quadrant and then write out the coordinate pairs that go with it. This one is 1, 0. The next one, remember the pi over 3 and pi over 6 have the 1/2 radical 3 over 2 coordinate pairs. This one is longer in the x direction, so that means it's going to be radical 3 over 2, 1/2. The middle one, remember, always has that radical 2 over 2 coordinate pair. The only thing that changes between the quadrants is the signs of the x's and the y's. And then this pi over 3 is 1/2 in the x and radical 3 over 2 in the y. And then up here we've got 0 in the x and 1 in the y. So it is helpful that if you can be able to just draw out that first quadrant, try to do these without looking at a unit circle. You need to be able to do that again without looking at a unit circle. So if you can even just draw out this first quadrant, that is going to be really helpful when you go to do the AP test. All right, so now that I did that, let's figure out what the sine of pi over 3 is. So we go to pi over 3. The sine is the y coordinate. That's radical 3 over 2. And right now, while you're just sort of refreshing yourself, if you do want to check by plugging in your calculator, just go ahead and type in sine pi over 3. Figure out what that is as a decimal. It gives you 0.866. And then just do radical 3 over 2. Make that a decimal just to double check yourself. And that is the same decimal, 0.866. So good way to check your answer. Again, you got to be able to do this without a calculator, but in this case, it doesn't hurt to check your work. All right, let's keep going here. So next one, the limit of the tangent of x as x goes to pi over 4. So we're going to just start by direct substitution. You probably aren't as familiar with tangent values. So what I would suggest is just writing this as sine over cosine. So it's going to be the sine of pi over 4 over the cosine of pi over 4. Think back to your unit circle. Pi over 4, that's a quarter one, so that means it's going to be the middle one with the radical 2 over 2's. So the sine of pi over 4 is radical 2 over 2, and the cosine is also radical 2 over 2. Anything over itself is just 1. And again, just to check yourself as you're getting back engaged into these trig values, just go ahead and type in tangent of pi over 4 into your calculator. Verify it. You do get 1. Again, don't do that at the outset. Make sure you can do this without doing that, but it's a great way to check your work. And so the next one is cosecant. So we wanted the limit of the cosecant of x as x goes to pi over 3. So it's going to be the cosecant of pi over 3. You probably don't know cosecant values off the top of your head, but remember cosecant is 1 over sine. So this is equivalent to 1 over the sine of pi over 3. All right, so at that point, you need to think about, well, what's the sine of pi over 3? All right, so think about visualize unit circle. You could even draw it again, draw that little quadrant. Sometimes I just try to picture in my head where that pi over 3 is on the first quadrant. Well, this one down here was pi over 6. So that means this one up here has got to be the pi over 3, right? And then think about the coordinate pair. I also like to think about, I know it's going to be 1/2 or radical 3 over 2. Think about the x direction. the x is going to be the shorter one in this case, right? It's the 1/2. And the y is up higher, right, and relative to the circle there. So that's going to be my radical 3 over 2. So if it's helpful, write these out until it gets stuck in your head. I still even like to have this mental picture and write it out sometimes as well. So the sine is the y coordinate. I also remember the cosine is the x, sine is the y, because the cosine, the c comes before sine in the alphabet, c comes before s, x comes before y. So that's how I remember it, if you're confused on that. So this is going to be 1 over radical 3 over 2. All right, now we don't want to leave our answer like that. That would never be the way an answer is written on the AP test. So we need to simplify this, flip it, multiply. So it's just going to become 2 over radical 3. That is also not an appropriate answer on the AP test because you never leave a radical in a denominator. So we need to multiply by radical 3 over radical 3. So we get 2 radical 3 over 3. That'll be our final answer. Again, to check your work, especially when we're in this online format and I don't always check, get a chance to check every one of your answers. Good idea to just go ahead and punch that in, figure out what that is as a decimal, 1.154, and then just go ahead and then plug in the cosecant in your calculator, which is actually, you're going to have to put in 1 divided by sine of pi over 3. Check your work there, and you do get the same 1.154. All right, just a couple more to practice here. Limit of theta tan theta as theta goes to pi over 4. I just switched the variable here just so you're at least just seeing a different variable. It functions the same as x, whether it was x or y. Typically we see x, but in this case it's a theta. Works the same way. So we just get pi over 4, tan of pi over 4. So we're going to rewrite the tan of pi over 4 as sine pi over 4 cosine pi over 4. We just had one similar to that. Remember that was 1 because it's radical 2 over 2, comma radical 2 over 2. So same thing over itself, so it'll be 1. So it ends up being pi over 4 times 1, which is pi over 4. All right, hopefully you got a decent handle on those. We are going to switch and do a couple inverse sine cosines. These are not as common on the AP test, but it is something that you should have a little knowledge on how to do. We're still going to plug these in the same way. So I'm just going to plug in 0 for x. I'll get the inverse sine of 0 plus 1 over 2. That's going to be the inverse sine of 1/2. All right, so this function's a little bit different. When you are trying to solve this, again, you cannot use your calculator for this. So there's a question you want to ask yourself. Remember that the domains and the ranges are switched. In other words, the x's and the y's are switched. So what this is saying is this is my y coordinate from the unit circle. Because remember, sine corresponds with y. And so instead of looking at this as an x, think of this as a y. Instead of looking at it as an input, think of it as the output. So instead of thinking like, well, what's the sine of 1/2? What we would typically see, think about, this is the question I want you to ask. What value on the unit circle has a y coordinate of 1/2? So we're kind of looking at the opposite, a flashback here. Before, we generally look at pi over 6, or we look at pi over 3, or pi over 2, right? We look at what's the coordinate corresponding with those. In this case, however, when I'm talking about the inverse, what I want to ask is, what is a y coordinate that's 1/2? And then my answer is going to be the corresponding unit circle value. So the y coordinate where there's 1/2, well, that's going to be right here, right? And so what I want to write for my answer, whoops, is the unit circle value, which is pi over 6. That's going to be my answer. So think about what y coordinate gives you to you, and that will be your sort of input is your answer. So you have to think in reverse. Everything about inverses is reverse of the original function. So that is going to be pi over 6. Again, it doesn't hurt to check that. You can just do on your calculator inverse sine of 0.5 or 1 over 2, and you should get 0.5235. Same as if you do pi over 6. Plug it in your calculator, and you do get 0.5235. So good self-checks, especially for these inverses. It's hard to like change your mind and thinking differently, but that's what we want to do. All right. This next one, I think I just realized I didn't do that the way I wanted to do it. So I'm going to skip that one for right now. I wrote that problem wrong. All right, let's look at the next one here. The inverse tangent of 1 when we directly plug it in. So we want to think about what tangent value is going to give us 1. All right, so this is a little bit more challenging because we have to think about essentially what coordinate pair gives us 1, right? Well, the coordinate pair is determined by an x value over a y value. Now, we had several examples of this where we ended up with 1 as our answer, right? So it's actually not that difficult when you consider the sine over cosine has to be the same because it has to give us the 1 for our coordinate pair, and that occurs at pi over 4, which I just realized this doesn't even have on there. Huh. That's our radical 2 over 2, comma radical 2 over 2. Did not copy a great image from Google. All right, so I'll upload a different unit circle. So that should be radical 2 over 2, radical 2 over 2. So if we're thinking of the tangent, that's going to be this one over this one, right? Sine over the cosine would give us 1, and the corresponding value would be pi over 4. So this will be pi over 4. And again, doesn't hurt to check it. Inverse tan of 1. And then double check that that's what you get when you do pi over 4. And both are 0.785. All right. My intent on this previous one was to make something where I guess the answer would be pi over 6, which would have to be a radical 3 over 2 or a 1/2. So I messed that one up. All right. Let's look at a couple other ones here. These I just added a little bit more to them, but they function the same way. So this next one, the limit as x goes to pi of this big function here with a square root and all kinds of stuff. Let's see if we can figure this out. We're just going to replace all of the x's with pi. So 3 times pi squared minus 1. And then the sine squared of pi minus cosine of 2 times pi. All right, don't get too intimidated here. The top, pi is a constant, so there isn't really a lot we can do there. We don't want to make it a decimal. 3 pi squared minus 1 inside of a radical. That's fine to leave it like that for now. On the bottom, one thing to note about just notation, this sine squared of pi, that's how we write sine of pi squared. That's what that means, sine of pi squared. Sine squared of pi, same thing. So what we want to think for this is what is the sine of pi, and then we square it, right? Now, as opposed to the difference here would be if our function was written like this, sine of pi squared with no parentheses, this would literally mean the sine of pi squared. However, that's not what we have. The reason we write it up there in front of it was because that's what tells us. Really, there's parentheses around it, but it's just an effort to eliminate parentheses. So this is wrong. So again, we want to think of it in that way. So the sine of pi If you can't remember what the sine of pi is, just draw a quick little sketch of what the pi function looks like. Or sorry, sine function looks like. Pi is right there in the middle, because remember this is 2 pi for 1 period. So that is actually 0. This is again the y coordinate of pi. All right, so that's 0. So this actually is 0 squared minus the cosine now of 2 pi. Remember the cosine function looks like this. So at 2 pi, cosine is up there at 1 again. So minus 1, sorry. So we end up with the square root of 3 pi squared minus 1 over 1. Or we can just write it as the square root of 3 pi squared minus 1. Oh, sorry, it should be negative 1. So negative out there. All right, and let's do another one here. This one is a natural log. Natural log function's exactly the same. We're just going to plug it in there. This becomes the natural log of 3 plus 4, which is natural log of 7. And let's just leave it like that. Natural log of 7 is a decimal, but we would rather leave it like that. 2 more quick ones just so you've seen some exponentials. Don't get freaked out by them. They just function exactly the same. If we were to do this e to the 2x, we were just going to replace the x with a negative 4. So e to the 2 times negative 4, e to the negative 8. On the AP test, you probably won't see that as an answer, e to the negative 8. Most likely your answer is going to be written as 1 over e to the 8. Because remember, negative exponents take it to the bottom of the fraction. One obstacle on the AP test is identifying the correct form of the answer. Because you might get an answer and that might be right, but that answer may not be listed in your multiple choices, so you have to rewrite your answer in such a way that it actually fits the given answers. So it's definitely good to practice that. Don't get lazy. All right, the next one, let's go ahead and plug in 0 here. So this becomes 1 over the sine of pi over 2 e to the 0. All right, so one thing to remember, if you plug 0 into an exponent, that does not mean 0. E to the 0 is not 0. Remember, any number or any constant to the 0 power equals 1, right? Anything to the 0 power equals 1, just the constant 1. So this turns out to be 1 over the sine of pi over 2 times 1, which obviously is just 1 over the sine of pi over 2. So the sine over pi over 2, well, that's the y coordinate at pi over 2, which is actually just 1. So 1 over 1, which is 1. All right, and let's end with one here. Go ahead and give this a shot. All right, so this is going to be just plug and chug here. Sine of pi over 6 over the cosine of pi over 3. So we'll just refer to our unit circle values here. The sine of pi over 6, that's the y coordinate at pi over 6, which is 1/2. And the cosine at pi over 3, the x coordinate at pi over 3, which is also 1/2. So 1/2 over 1/2 is 1.